Thanks everyone. I'd originally told Vinny that I'd talk about net zero. The term net zero is often now sort of being disputed. So I'm going to talk about as a low carbon future or lower carbon future. And so if you can bear with me on that, it's sort of a bugbear that we don't, as a human species, we don't do anything without having an impact somewhere. So to say that we can have a zero impact, I think is a bit of a fallacy. I'm not sure how many of you are familiar with the Canadian Wood Council. We're a technical support organization. We don't sell anything, but we work to enable wood to be used appropriately in an increasingly, I guess, interested world that is focusing on carbon. But if you have questions about education or training or technical questions about codes or standards or fire or a structure, the CWC is the sort of go-to organization, and the services we offer are free. So for this presentation, I'm going to start with what some heavy and mass timber products are, how they're made. Then we'll look at some of the regulatory changes that are affecting mass timber in Canada and around the world, carbon and what the wood industry is doing, and then some of the uses and buildings that are constructed with heavy and mass timber, and maybe look at some of the areas where mass timber can go. So we're all familiar with the traditional light frame construction, houses, low-rise commercial buildings, et cetera. And that's using a traditional product. But there are also new uses for traditional products. And when I think of something like that, I'm looking at mid-rise construction up to 6 stories. Some of you may be familiar with those. Some of you may have designed some. These can be done in either panelized or modules. So there's an increasing opportunity to use traditional wood products in new uses. There's also new products. CLT and is a new one. CLT is one of many mass timber products. And we're finding both traditional uses in low-rise commercial, 2-3-story buildings that might have been able to be built with light frame, or that were only allowed to be built with tilt-up or precast concrete. And that can be, we can now use mass timber to displace that. We also have some new products and new uses. I'm looking at mass timber. I'm looking at wood fiber insulation. There's 3-ply boards. There's a number of new products that are increasingly being used in Europe and around, or in Canada, that are also going in new buildings. This design here is a 12-story passive house building that was designed in a Esquimalt. This is a 14-story building in Quebec, and the building was completed and it was using mass timber. So traditional products, traditional uses, new products, new uses. It's a tremendous opportunity for wood. From a mass and heavy timber, we're probably familiar with some solid sawn timbers. We see those if you've been to Europe. You'll see some old cathedrals and stuff with like this hammer beam system in Europe. On the right is a heavy timber with a nail laminated timber decking, and that's in a building. It's about 100 years old in Vancouver, 120 years old in Vancouver, and that's not uncommon. From many years ago, and that's this building that I'm showing you from is a 9-story building built in 1905. So sometimes we think, gee, we're building tall wood is a new thing. It's not so much a new thing. It's that we've forgotten that we did know how to do it. We're just sort of getting back to that. It's a bit of a renaissance for wood. The product I mentioned, nail laminated timber, is mechanically fastened. It's long been used since we developed nails to make larger slabs of wood. Fairly simple process. It can be done on site, but increasingly is being done in panels that are then shipped to site. Glue laminated timber been around for 80 to 90 years, and it essentially uses smaller pieces of lumber that can come from smaller trees and are laminated together with a structural resin that can displace heavy timber and makes better use of the forest resource, either because it can use smaller trees or because it uses less wood overall compared to solid wood. Laminated veneer lumber, very similar veneer as that used in plywood, but the veneer is all oriented in a single direction. So LVL, you probably used it in headers along with LSL and some of the other engineered wood products if you're using light frame construction. But it is also a mass timber product. It can be glued together, and it can also be, in some companies will make it thicker. Laminated strand lumber, oriented strand lumber. These are also composites that have smaller pieces of wood, resin, pressure or extrusion, or either by plates or by continuous process, and can create a product like all mass timber products that are consistent in performance and consistent in cost, so that the first lineal foot of a product like LSL is the same price as the last lineal foot. Parallel strand lumber is probably the strongest engineered wood product. It uses long strips that are coated with the PRF resin, put under pressure, extruded through high temperature, and produced in 64-foot lengths, which can then be resawn. They can be glued together. They're excellent as columns or posts. It's more expensive, but it's about 3 to 6 times the strength of a conventional solid wood product. So these are all mass timber. CLT is sort of the poster child for mass timber. It uses the traditional dimension lumber and then is glued in cross laminations. It's been around for about 35 years in Europe, and around almost 15 years, well, 13 years in Canada. But it has the opportunity to displace other solid panel products, whether it's precast or tilt-up concrete panels, because it has a lower embodied impact, and we'll get into that. Others that are out there now, dowel laminated timber, very similar to the mechanical fastening of nails, but it enables a CNC to cut an opening out for a door or a window without encountering nails. And then mass plywood panels, MPPs, are only produced in a plant in the United States, but it's an exceptionally strong and versatile mass timber product. There's mass timber products or plants all around Canada. We're constantly shifting and changing and growing. Companies are either are establishing themselves as new companies or are expanding their facilities to meet the growing demand. None in the Maritimes at this point, but I think we'd like to see that change, and I know that there are some efforts going forward to make that happen. So one of the things that is increasing is there's a fully integration. It's possible to fully integrate our value process for wood products, and I think the industry I know is looking at mass timber. They're looking at wood fiber insulation, and they're looking at what the future uses of these products can be. So we look at mid-rise construction or tall wood. That's going to require a different product than a high-performance single-family home. But the products that can come from a log include solid and also fibrous components. The fibrous components that can't be used in a structural product or a long-lived product can be used as an energy source to displace fossil fuels, and that is increasing, as well as looking at wood chips or wood products that maybe we don't want to put them into paper or newsprint, which is relatively short-lived, and we can make them into either products like an OSB or an LSL or a wood fiber insulation product, which is quite common in Europe, and all the facilities are increasing their production. So I want to talk briefly about one facility. It starts as a sawmill. It makes solid wood. It makes laminated decking and posts and glue lam, cross-laminated timber boxes or sort of torsion box products out of wood. It also makes pellets and energy, electricity, steam, heat, hot water, refined fiber, and wood fiber insulation. And it's all in this one plant in a small town in Germany. You can see the town in the background. That plant was an old sawmill, was a sawmill for 100 years, and then they started growing and diversifying, and now they make all these products in that one facility. And this blue roofed building here was the original farmhouse from 100 years ago that they've modified. So that the potential for really utilizing our forest resource is amazing. Some of the opportunities I'll take you through are the regulations that are changing. We'll look a little bit about construction capacity, changes in technology that are advancing both in design and wood. Some of the social issues that we face, whether it's affordable housing or the fact that we want buildings to be good for us, and we'll take a look at perhaps some of the things that wood can contribute to, like designing for deconstruction in the circular economy. So first, let's talk about carbon. Um, to deal with wood, you have to start in the forest. We've often said that the benefits of wood are they sink carbon in the forest, they sequester it in buildings, and it can be substituted for other materials. That's the 3S concept. But it really starts with sustainable forestry. And sustainable forestry in Canada is something that we have done very well. It's not perfect. Anything that's done by humans, we're going to screw up. But for the most part, the certification levels that we have in Canada are as great as the next 10 countries combined. This was a certification globally around at the end of the year. Many of the areas in Canada are double certified. Those have been removed from this, but we can be justifiably proud that we have a very high level of forest management, even if it's not perfect, and it will never be perfect, but we constantly improve. The other thing about forests that we have to look at, especially these days, I know in the Maritimes there's been forest fires. I live in British Columbia. We have forest fires here. That is a release of carbon. And it comes from, it's basically an artifact of climate change, but we have to look at the forest carbon in the context of what the forest does for us. The forest stores carbon, it produces wildlife or has habitat for wildlife, stores water, and produces wood products. And you may encounter that there's several sort of let's just stop logging or let's convert all the forests into buildings. The carbon budget model developed by the National Research Council and Natural Resources Canada has been looking at what's the way to optimize carbon uptake and carbon benefits. And they looked at bioenergy. They looked at harvested wood products and long-lived wood products. They looked at harvest reduction and conservation, optimization of the forest resource. And they found that if we're looking at carbon, we need to do a little bit of everything and do it really well. There's not a single solution that turn it into buildings or leave it all standing. None of those will optimize the carbon benefits that our forests offer. The carbon budget model is available online. You can go take a look at it. But as you can see, there are different, it's a parametric tool that looks at all the different elements that go into determining the carbon benefit of wood, from energy displacement to conservation. So, but there's also operational impacts, and that's basically high performance in green building. The federal government has indicated that they are going to be adopting a pan-Canadian framework that leads to zero energy, and will have a requirement in the 2025 building code to look at the carbon emissions associated with energy. And in 2030, the building code cycle will bring in the carbon emissions associated with the embodied energy into wood products and other construction products. So the government is moving quickly to recognize the carbon impacts of construction and their own procurement. And we're seeing that in local governments and provincial governments as well. It's not just reducing the energy use, it's reducing the environmental impact of building materials, and they'll be using life cycle analysis. Normally I'd ask people, who in the room has done an LCA. I can't really see that, but it's not just in Canada that we're trying to advance the life cycle impact assessment. We're seeing it in Europe. In Switzerland, they were the first to have a plebiscite to look at a maximum energy use for people. Germany has whole building LCA requirements. Belgium went from having one of the lowest sort of performance indicators to having one of the highest by requiring passive house construction. So this is not just, the decarbonization effort is not just happening in Canada, it's happening around the world and often led by Europe. I talked about embodied impact. That impact is essentially what goes into making these products. So we'll talk a little bit about that. Earlier, I mentioned the different aspects of wood and how it can have a carbon benefit or a carbon emission. if one focuses on just on the forest cycle, the, there are three areas. This was a research done at the University of Washington, and it looked at the the growth of a forest. This was a model based on the annual life cycle or potential life cycle of a tree. As a forest grows, it increases its carbon, and then when it's harvested, it loses that carbon from the forest, and some of it remains in the forest in soil, some of it remains decays over time, and some of it is in solid wood. But over time, a forest will reach a stasis. We're finding this in the boreal forest. We're finding this in some forests in British Columbia. They store a lot of carbon, but they're not storing any more. They've reached a point where they are stable, but they're not increasing their carbon. So the forest will eventually reach a stasis. If there is harvesting of a portion of that forest, then you can have both the carbon sink, but you can also have sequestered carbon. And that's the carbon that is stored in products, whether it's furniture, whether it's books, whether it's buildings. And these buildings will last various lengths of time. So that's why the slope of carbon uptake is less than that for the forest. But a real important consideration is that if you don't use other materials, you're avoiding the emissions associated with those. At this point, I'd like to say wood's not a perfect material. If it was, we'd all be building with it, and Vinny and I would not have jobs. But it's incumbent on us to look at whether a material it has a greater or lesser impact. And that's where the building code is going, and that's where we are as an industry are going. We're looking at how do we reduce the carbon impact of our product mix, whether it's concrete, whether it's steel, whether it's wood. So life cycle analysis is increasingly important. It's increasingly common. It's not easy to use. I mean, some of the LCA tools are complex. There's several different tools out there. Each has different assumptions and different ways they treat a material at the end of life, or in utilization, or in life cycle, or in lifespan. But one of the things I wanted to point out was an LCA that was done. This was done in Australia. And over the course of a building, and this was for all materials, it was found that the embodied carbon was about 35% of the total life cycle carbon. The part of the carbon that was associated with the energy efficiency standards totaled just 24%. So you think about that. We regulate the performance of a building and the building envelope and its structural integrity and seismic and fire resistance and all that. But the parts of the building that are associated with carbon that are regulated account for just a quarter of the total carbon. We don't regulate how long a shower is for people have, or how much they cook, or what kind of equipment they have that they use. So, but this points out that embodied carbon is an important component for us to look at. And we can't just focus on the energy performance. We have to look at the whole life of the building. There's a tool that was developed for the Quebec government a few years ago. It's called Gestimat. In Ontario, it's GHGMAT. And it looks at actual building systems that are used in Quebec and in now Ontario, where they say, what are the typical construction systems? They took those systems and determined what the environmental impact is of all of the components. So for a steel concrete solution, you're going to have an open web steel truss, for example. This is one of many systems. You'll have decking, you'll have rebar, you'll have concrete. Each of those has a quantity or a mass, and that collectively produces the environmental impact. If we look at wood, it also has environmental impact. You've got to have the wood, you've got to have the nails, truss plates, OSB or plywood. So all of these different systems have an environmental impact. The use of LCA and tools like Gestimat or GHGMAT or other LCA tools help guide us into the approaches that we may take. And as mass timber comes into play, it's able to be incorporated in more building systems, whether it's a floor plate, whether it's a wall system, whether it's a structural interior wall, a glulam beam can be a column. So it's going to be important for us to have an understanding, not just of the impact of a specific material, but the impact of that material in use with other materials. So I'll get into that a little bit later. But in the long term, the IPCC recommends that we've got to have a sustainable forest management strategy. We want to increase the forest carbon stocks either by growing more forest land where there used to be forests but aren't, or by incorporating sustainable wood products into long-lived products. And that will be the largest sustained mitigation benefit. It's not just a reduction, it's actually a mitigation. It can, by removing the CO2, it can actually store that from the environment. So I talked about embodied impact. This is a model that was done, and we've simplified it a lot, but over the life of a building, in this case, we chose 80 years with a variability that the USGBC has identified of about 12 to 20%. So we chose 15%. Operational is the red, embodied is the yellow. Here's the thing. When you build a building, the embodied impacts are done. You cannot undo those. They are embedded in the building before you even turn on the first light. Over time, as you operate the building, you add impact. Year 1, year 5, year 10. In this particular model, at year 12, with 15% and 80-year life cycle, the embodied equals the operational energy. After that, the operational energy dominates. However, there's things that may not always be reliable. Is the building well maintained? Was it well operated? Did the owner get tired of it? Did the land value come up where you say, hey, you're telling me it's worth how much? I'm out of here. And a perfectly good building can be torn down. And we see that happening, especially where I live in near Vancouver. A perfectly usable building gets torn down because the land has more value for something else. So these are all variables that could extend or reduce the life cycle of building. And the future is very difficult to determine. So we do need to pay attention to the embodied impact. One of the things about wood is that it's classified as a biogenic material. So we know that over time, that wood is likely to go back into the atmosphere. Very few buildings are going to last 1,300 years, like some of the, a couple of buildings I know of in Japan and in China. But even the delayed emission, which is how biogenic carbon is treated, has a benefit over time. So we have to recognize that maybe the benefit now by sequestering and storing carbon will give us time or extend before the tipping point until we have reached some other solutions. With respect to wood, this is some work done by Dr. Annie Levasseur, calculated that the net present value of a ton of wood now is equivalent to 4 tons in 80 years. Just like a pension or investment plan, put $1 in now, you hope it's worth a few dollars in 80 years. That's the carbon benefit, and that's the benefit of a delayed emission. So let's talk a little bit about energy use. This is a mass timber building built in North Vancouver. This is the artist's sketch at the beginning. It's 3 stories. It's not a complex building. It's an infill building, 24 feet wide, mass timber, glulam, and light frame passive house panels. No basement, no underground parking. And the owners chose to use this wood because they wanted the building to be resilient in an earthquake. They wanted it to be high performance. They wanted it to be comfortable, and they wanted it to look nice. This is the completed building. So this kind of building is probably very repeatable in most cities around North America. It's an infill because it's zero clearance on the back wall. It's 3 stories. The structure took 10 days to erect. I was on site most of those days taking photos. It was a very impressive and fast little building. So those of you in the construction sector who've ever built a mass timber building probably get the opportunities from speed. But again, this is the direction of our codes around environmental regulations, and that's an opportunity for wood products, partly because wood has thermal performance values, but also because it has a low impact. So what we did is we took that same model we used before and applied a passive house level of energy use to that building. So passive house buildings or high performance buildings typically have a slightly higher embodied impact, as shown here. It's about 15% more materials are used, typically in the envelope. So we had to account for that. And then we started looking at the operational additions to that. With a passive house building, the incremental annual operations are much smaller. So year 5, year 30, year 80, we still had not reached equality between embodied and operational, such that the embodied impacts after 80 years for this model was 54% of the total life cycle carbon emissions associated with that building, which is about a third of the overall impact of a conventional performing building. So operational performance and embodied impact from from materials, they both need to be considered, and they need to be considered at the same time. What we're talking about today are some of the changes. We're doing this across the country. Sorry, this is I took a slide and didn't realize there was a video on that, but this is we're doing a life cycle survey of these 5 products around the country. We've got truss companies, lumber companies, plywood companies, OSB, you name it. And we're gathering the life cycle information so that we can contribute to the life cycle inventory of the database that is being developed by the National Research Council. So for those of you who may not be familiar, there's several stages in life cycle analysis, starting with where a product enters the system. All materials have to be extracted. So what are the impacts of extraction? Whether you're mining, whether you're logging, whether you're harvesting on a field, they all have an environmental impact in their system. And as you go through, you have to manufacture it. There's also replacement products. There's transportation impacts. And at the end, there's combustion, landfill emissions, end of life, recycling, all of those things. So for the work that we're doing, we needed to look at the extraction of raw materials, the wood products, the transport to the factory, and the manufacturing of the products. At the end of the manufacturing, it moves into the next boundary. So transportation to site and then construction use. So what the life cycle inventory that we're doing for wood products, which will be available and uploaded to the database in 2024, and it will be available for designers to access. It's run by the federal government. They're using it for their own procurement, but it's going to be available to designers because they design federal buildings. So this kind of information will enable us and designers and procurers to say, what's the carbon impact of my building? The Wood Council often gets involved in helping people design, but we don't get involved in actually constructing the building or using and maintaining. But that's another area where choices made there will impact the embodied emissions because of choice of material. As I mentioned, there's no perfect material. And I think that we're going to be looking increasingly at hybrid design. Wood, steel, concrete, glass, aluminum, every building is already hybrid. But there are structural systems that can really reduce the impact. And that's where heavy and mass timber can play. And at the end of the day, we would like to see more a circular approach. And mass timber can be deconstructed in the built environment, but it has to be planned for. And that's where you come in as designers. If you don't plan or don't anticipate that the building could be taken apart, it's likely it would just be demolished and salvaged. So this is some work that we're focusing on with the National Research Council in their LCA squared. That's low carbon assets through life cycle assessment process. And we're focusing on the A1 and to A3 product stages. So technology and codes. The Wood Council gets involved in codes. We don't get so much involved in developing technology, but that is changing as it for wood. With the codes are allowing taller wood buildings. The codes are requiring higher performance. And in the case of taller wood buildings, it's usually an issue around fire. So there's been several fire demonstrations and fire research projects done in Ottawa and in British Columbia that look at just how well does mass timber perform. picture here was a fire demonstration we did in 2017 for fire officials. And the research looks at what's actually happening in the wood. Here, after an hour and 15 minutes, you can see that we had about 3/4 of an inch of loss in the ceiling of that DLT mass timber roof. Here, you can also see the same. This was a glulam beam that was inside the burning structure. And after an hour and 15 minutes, the side that was exposed to the flame had lost about 3/4 of an inch, and the side that was exposed to a flame going past it was about half an inch. So fire has the understanding of wood and fire has enabled code officials to say, okay, if you have this much wood, we know that it will be safe to the occupants so they have time to get out, and to the firefighters who might go in. So another thing that is becoming difficult, and if some of you are in the construction sector, I see Rick Burr was on the participants. Hi, Rick. As a contractor, I think looking at prefabrication and construction capacity and industrialized production is something that is very much front and center. So wood elements are generally, if they're heavier mass timber, are generally prefabricated. They don't show up and have guys with chainsaws manipulating them on site. The picture on the left was an elementary school built in Vancouver, put by the Vancouver School Board, all prefabricated elements. They were all just dropped into place and connected. On the right-hand side is a box beam that was created in a company in Finland. Again, prefabricated and just installed. So this is really a key aspect to wood products. They can be machined to very tight tolerances, prefabricated, delivered on site. This was a building that was built during the late fall winter season. You can see the picture on the left had snow. That was taken the day after the picture on the right. So, but it still proceeded and went up in 7 days. So the other thing that the construction sector is facing is labor shortages. In BC, we have tens of thousands of jobs in the trade sector: electricians, plumbers, framers, foundation people, envelope people that are in short supply. And I know it's the same in the Maritimes. I know it's the same in most of Western Europe and in North America. That means that we have to increase productivity. And productivity is different from production. Productivity is the amount of, I guess, work accomplished by every individual worker. That's a big issue. The construction sector has had fairly low productivity over the last few decades. In fact, when one looks at the productivity of the construction sector, it's one of the lowest. And since 1947 until 2010, the productivity growth rate for the construction sector was 0.1%. 0.1%. Who's going to make an investment into that? Part of this is that I think is the complexity of the buildings and the expectations for our buildings. It takes longer to produce some of these buildings, higher performance expectations. All of this, these are reasons. We can't use them as excuses. We have to look at solving them. And this is where heavy and mass timber can come into play. Technology is also impacting wood product development through resins, the chemistry of resins to make them either lower impact or make them more durable or make their faster setting. And then there's the technology around the software that is used in designing buildings, whether it's fire modeling, whether it's seismic modeling, whether it's direct to machine machining for wood products. That's all enabling us to have a better productivity, faster construction, and more accurate construction, which leads to tighter joints, lower air loss, and better energy. So all of these are interconnected. This was the joint on the left took 4 minutes to produce, and it was at a company that I saw in Finland. Now I look at that joint, and it was quite impressive. And I thought it would take me a week to do that. As a woodworker, I would take a week to do that. A traditional timber framer would never consider a joint like this because it's just too difficult to do. But the technology that is available now in machining wood and the tolerances that wood delivers are really, really valuable to contractors, provided you get the system right. And I talked about labor shortage. We need detailers. We need engineers. We need architects who understand the opportunities and the potential for wood and have the technology to deliver that right through to the manufacturing and the construction on site. I'm not going to talk about virtual construction and also building information modeling. This it's something I'm sure you're all more familiar with it than I am. But this particular sequence of pictures was done for Brock Commons 7-8 years ago. They pre-built the building, and that helped them with their efficiencies, the order of operation, safety issues, emergency egress issues, crane use, all that kind of stuff. Many wood buildings now, especially the mass timber buildings, are using this technology, but because it gives them a heads up going, oh, we better not do that at this point because we can't insert the next piece. And I know of several buildings where the contractor, the trades, the installer, the client are all working to make sure that the approach for construction is accurate and fast and safe. So some of the social issues which are opportunities for wood. I think one of the biggest issues that we face, and you saw yesterday, the federal government even switched out their housing minister. Densification is happening because land is less affordable. People want to live in cities. A lot of cities can go up or they can go out. Cities like Vancouver have to go up because they're bounded on 3 sides by water and 1 side by another city. So that creates densification. At the same time, the building codes are requiring that these buildings have a higher energy performance. We're also concerned about affordability. So the whole issue around housing is an opportunity for wood products. The picture there is a passive house building on Fraser Street in Vancouver. It was called Skeena. It's 6 stories, but it's stepped. And so the bottom it's a whole block long. This is the top and it's 4 stories, but it steps down twice. So it's classified as a 6-story building. Light frame construction, passive house performance, and it's half affordable housing and half market housing. So it uses mass timber elevator shafts that can just be dropped into place. So the social issues that we are facing as collectively have some solutions that can be found in wood. The BC Housing Organization, it's a crown corporation of the provincial government, is looking at incorporating wood in higher, taller buildings. And these are a couple of proposals that were nominated, and I think the one on the right was accepted by BC Housing, and it's now going to Greater Design. But they're prefabricated and they're mass timber. They're not just mass timber. It's a hybrid construction. Mass timber elevator shafts are found in virtually every mid-rise project in British Columbia and in Ontario. They're moving to that, but in Ontario they stick to mostly concrete. In British Columbia, we have 950 buildings that use wooden elevator shafts. In Toronto, there's a couple of mass timber buildings that use mass timber elevator shafts, but the difference in speed of construction and ease of design with an all-wood building versus a mixed building has demonstrated itself in the mid-rise sector. On the left, it's an NLT mass timber elevator shaft. On the right, it's CLT. The CLT one that we see here was 3 stories were dropped into place, and it took about 15 minutes to drop a 3-story elevator shaft that was fabricated that was assembled on site and dropped into place. I talk about hybrid design and hybrid systems. You can see here, light frame is used with concrete. Light frame is used with concrete and mass timber. Don't be afraid to mix these systems. The more common way for mid-rise structures now in British Columbia is light frame vertical walls and mass timber floor plates and light frame envelopes. The mass timber floor plates get dropped into place. They provide immediate working surface, easier to install. You don't have 2 guys on ladders putting in I-joists. So it's just increasing. We're seeing that this is a way to use it in a fairly standardized approach to construction. Several of the new commercial buildings, office buildings, are also moving to having steel beams or steel columns. Even the Fastenep office, and Fastenep is known for their wood engineering, uses a mass timber and has wall system, has glulam beams and steel columns. Why? Because in this case it was cost, it was also space, it was also availability of material. So mixing and matching steel and wood can be a very efficient, very effective way to advance a building that deals with the affordability as well as the speed of construction and the operability of the building and the floor space. The building on the right is a finished building. This is it on the right here. They had mostly all prefabricated elements, including these 2-story, 1-story, and 3-story balconies that were slipped into place on the finished exterior with using a steel dovetail. And they had to be prefabricated because the accuracy of those dovetails was essential to the structural integrity and the building envelope, because this was also a passive building. So CLT and mass timber products can be used outside, but you have to detail it properly. In this situation here, you've got attached CLT balconies that are protected by a cladding and a lip here that protects it from water ingress. Increasingly, we see industrial buildings in Europe that are using heavy and mass timber systems. This is a beach LVL product that can be imported into Canada, but it's very strong, but it's quite expensive. But it made sense because all of these trusses, prefabricated, assembled off-site, delivered on-site. And this is a company in a small town in Germany, and the product that they're making in this industrial facility are screws for mass timber buildings. There's also non-structural use. Nakoon, which is the building company that built that 3-story passive house in North Vancouver, made stairs. There's no metal connectors on these stairs. They used a new resin called TS3 that enables rapid construction. It's structural and it doesn't burn. I was completely amazed when I saw a test result that just the only thing left after combustion was the resin. So there's an architect in Toronto, Ty Farrell, who has recently completed a master's of neuroscience in architecture. Who knew? And he has long used wood for its healthful benefits in hospitals, care centers, education centers. And the reason he took the master's was to better understand the conscious and subconscious role that materials and our buildings play on us. Whether it's a sound, a buzzing that we may block out, still our body has to block that out. Air quality, whether it's particulate, temperature, moisture, natural light, and also the materials that we use. Increasingly, there's research that talks about the health benefits and the reduction in stress levels of heart rate and sweat with exposed natural materials, be they stone, wood, plants, natural light. So Vinny's going to be sending this out. If you really would like to explore this, there's a very good document that was produced on wood well-being and performance. There's a few of them around. It's available at the Naturally Wood website, and it's free. So this is an area where we need to consider, are the buildings that we're designing helpful or harmful? As I say, Ty has used this in several hospitals and in colleges around. And they've got an incredible website if you want to look at it. He understands the health benefits of wood and as well as the increasing in performance and productivity of a wood building. Finally, nearing the last few slides, designing for deconstruction. I mentioned at the beginning that there's a role that has to be played by all of those in the value chain of construction, architects, engineers, and designing for deconstruction is a very critical part to extend the life of the materials that go into our buildings. And there are a couple of standards that have been developed in Canada for deconstruction of buildings and design, but we're not there yet. But mass timber has an opportunity to increase increase the potential for deconstruction. Mass timber buildings are fastened by mechanical connectors. They're not cured, they're not welded, they're not, the mass timber is glued, but the mass timber buildings are not glued together. This is an excellent opportunity to have design and reuse of buildings. This is a building that was built in Italy, deconstructed, sent to Japan, put on an earthquake table, subjected to several earthquake tests, and then removed, taken back to Italy, built as a student residence, and then deconstructed and used as a kindergarten. So the benefits of deconstruction are very similar to the benefits we find with mass timber and prefabrication. So if you're considering buildings that can be, and you want them to be reused, take a look at some of the mass timber connection systems, the mass timber products, whether it's, as I say, modules. I know that there's some prefabricated buildings in PEI that are module. And these kinds of buildings do have a chance to be taken apart. So where can mass timber take us? This is a schematic of a 12-story building in Langford. Wood was chosen for its cost competitiveness. The builder has some market and some affordable housing. The builder's also the developer has done a 7-story building and several 6-story mid-rise, and moved from 4-story mid-rise to 6-story mid-rise to 7 mass timber to 12. A couple of years ago, I had the opportunity to be here. This is the top floor of that building as it was nearing the structural completion. So it's a mix of steel and wood. There's a company in British Columbia called Intelligent City. They're using mass timber to make prefabricated high-performance wall systems for multifamily and affordable housing. So these are elements that I think we have to look at, is how mass timber can contribute to what we need, not just using it because you like wood. That's fine. I'm a wood geek, but look at what the product can deliver for what you need. Is it performance? Are you trying to have low carbon? Do you need speed of construction? Do you need accuracy? Are you focused on cost? There's a whole bunch of different systems out there: solid wood, hybrid construction, light frame. Take a look at those. One of the biggest fears we have is wood rots, it burns. Here's the building I mentioned earlier. It's 1,300 years old. Designed in an earthquake zone, a typhoon zone, fog, wind, rain, high temperatures. It's an unconditioned space, but it was built without metal connectors. One of the things I'd like you to consider is that materials will only do what we ask them to do. And they don't fail us, but we may fail them. If we design a building, whether it's a wood, steel, or concrete building, and we don't understand what that building is going to face, it will fail. So we have to understand how these materials work together, how they can be integrated, how they can perform to optimize what we need them to do. And if we don't do that, we're really sort of not doing our profession, our clients, and our environment the due diligence that we should. I'm often asked, why would I build with wood? Well, it's all of these things. If there was a material that was a carbon sink, renewable, reusable, recyclable, biodegradable, it cleans the air, cleans the water, provides habitat, avoids CO2, it's strong, lightweight, all of these things, I'd be rich. But we have trees. And so the question maybe shouldn't be why wood, but if not wood, what? If we're going to build, what do we need to consider, and what are the choices that we have?